Так, следующий мок начался в 6:00. Пока что ожидаем. Задачу я спрашиваю, а собеседник тоже на дерево. Nice.
Great. So you're familiar with Pramp? Are you familiar with Pramp?
Yeah.
All right, cool. So it seems that it's your turn to solve the puzzle.
Okay.
Yeah,
Okay, so let me read the problem.
sure.
Array, string array, combine function that should be substring that finds the small substring all. Okay. Okay. Substring. Okay, so we are given a string str, which is basically like some characters, and we are given some unique characters in a character array. We need to make so we need to implement a function that finds the smallest substring of str containing all the characters in array. Oh, so okay, return empty string if it does not exist. Okay, so okay, so we need to find like the smallest substring such that all the characters in the array are present, and we need to return that substring, right? Okay.
Correct.
Okay. So they all should be. Okay. Oh yeah, and all characters are unique. Okay, so there are no like duplicates. Okay, and if it's like doesn't exist, we need just to return empty string. Okay, so for this solution, they are all unique. Okay, so we can try to solve this solution by using a sliding window on this str string. So
Sure.
we move like from left to right, and every time like each character we add this character to the window. So for instance, we say like we start from the left, so we add like x, y, and y, and every time we see every time we see a character that is already in the window, so like I, there is no way we can have like two in a row or like two in total because there is only one I and all the elements are unique. So every time we see like a duplicate, we just shift the window to the right, and we repeat the same procedure until we find this substring. Otherwise, we just return an empty substring. Empty string, right?
Sure.
So for
What
this,
do you mean every time you see a duplicate? So Y and Y are duplicate in str.
yeah. So like duplicate. If we look at the array, there is only one y character.
Yeah.
So there, no. I mean the in the array.
Correct.
Yeah. So in the array there are all unique, but in the string there is no way we can have like two i's or two x's in the same substring. So every time so as our window gets bigger,
Right.
and every time we see the same element we seen before, we just shift it to the left, and
Yeah.
so like to satisfy this condition.
So if I were to change this problem, when this is fine, it's a very good start. Say instead of using X and the end, I switch X and Z essentially.
Sure. Yes.
I'm sorry, X, Y, Z. So this is Z. So that the only possible substring which contains X, Y, and Z is X, Y, Y, Z.
Uh,
How do you suppose your solution handles that?
so our like substring can have can oh so For this
Yeah.
problem, our solution can have like duplicates within the substring, right?
Yes.
Oh, okay. Uh, yeah, in this way, like this approach is not correct for uh, this like input. So yeah, in this case, let me see. So, okay, so we need to return like the window that contains all the elements. So within the substring, within the substring, so for instance, like x, y, and z. So in our substring, there should be only b, x, y, and z. So no other characters, right?
Yeah.
Okay. 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 Hmm. Okay. So yeah, I mean, like, what comes to mind is that we can just start from the very beginning and go to the right until we get the substring which contains all the elements in the array. Uh, and like, but yeah, we need to find like the minimum, right? So
Yeah.
we get some substring and we say like this is our minimum. Then we start like from the position 1, do the same, position 2, like repeat all the operations. So sounds like an squared solution, which is like not really efficient
Yeah.
because we repeat the same operation for all characters.
Yeah.
Okay. Okay.
What can you say in this pattern when so this pattern is expanding the current string that you're looking into, right? So you have left pointer and the right pointer, a sliding window.
Mm-hmm.
And you basically keep on checking if the substring that you have built so far has all the characters in it, right?
Oh, yeah, I think there is like a better solution with a sliding window. Oh,
Yeah.
yeah, I have an idea. Right.
Sure.
So we can like use two pointers. So until we have all the characters, we just add them to the window, and yeah, we just populate our window until we have all the characters. So we add like x, y, and z.
Correct.
And in this case, we have all the characters. So we say that this is our solution so far. Uh, in this case, we just save it as our like result so far, and
Yeah.
then we just shift our left window to the right. So our
Correct.
window is YYZ now,
Yeah.
and we go to the right again. So we go to like YYZY,
Yeah.
Z, Y, and X.
Yeah.
Here our solution, like we found the solution, but still it's too long, and uh, then we just shift it to the left.
I don't think other than the very first XYYZ, you're gonna find any other solution which has X in it. There's only one X, which is at the
Oh
beginning of
yeah,
the year.
yeah. So this example, right, is just these like four characters in the beginning.
Yeah.
Oh, okay. Uh, yeah. So if we do like sliding window approach, we
Yeah.
do not. Oh no, we actually should allocate some memory, and for this problem, it should be set. Yeah, set. It should be set. So uh, and the size of the set is the size of character like this array right here. Uh,
Mm-hmm.
yeah, and that's memory complexity, and the time complexity is just linear, which equals to uh, length of the string.
Are
So
you sure that it's linear?
um,
For
yes,
each
yeah,
character, we're trying to expand
Yeah.
such that it contains the whole array.
Mm-hmm.
And that means, are we not looking at some characters multiple in the approach that you have discussed so far? We start off anytime we have completed one substring which contained all the characters, and then we shrink it from the head, from the starting point,
Uh,
move our head character by one, right?
yeah, but
And then,
mhm.
yeah,
Yeah.
and then
So
what do we do?
uh, yeah, for this solution sounds really efficient, but like what I uh, what I suggest is that we just do it in a linear way. We just like have pointers like I and j, like front and the back of the window, and
Sure.
just we will add some conditions like when do like the window shrinks or gets bigger, and yeah, we can get
Yeah.
result is just on linear time because we just do one like slide through the string. No like inner loops or anything.
Okay. So you think your code is solving it in linear time?
Uh, yes.
Okay. So let's see the solution.
Okay. So let's start like from the beginning. We will need like a set to contain like characters we have seen so far. So we need to
Yeah.
like a set of characters. Uh, okay. Okay. So we have like pointers I and j which are equal to 0.
Mm-hmm.
uh, then we start like until j is I mean while j is less than the strength length of this string, we
Sure.
just like go to the right. So so j is always like in front. Okay, so yeah, we add the next character to a set. Then there also should be okay some condition like how to find out if we have all the elements in the window. So for this one there should be a variable called like size, which equals to length of the array. So
Mm-hmm.
like for this example is 3. So we say we see x, we add it, so then it gets like to it becomes 2. Then we add a y, it
Mm-hmm.
becomes to 1. Then we see another y, but it already is in the window. So check if character is in a set. If yes, size minus I mean just decrement it.
Got it.
Okay, next step. So yeah, we add like x, we add y, we add y, okay, and then we add z. Okay, we added size decremented. Oh, and yeah, when size equals to 0,
Mm-hmm.
it means that we found the substring so far,
Yeah. Yeah.
and we just need to save it somewhere. But uh, we also need to like because that should be the smallest. So we need like to have
Right.
some if statement here.
Sure.
So for if statement, okay, we yeah, I mean if current window is less than result, we just swap them. I mean just yeah, make result equal to this current window, which is like the best so far.
Okay.
And then okay, so for like the example in the problem, we have like x, y, and z. Then until yeah, oh, and yeah. So next step we just okay. we get the left character, so character left equals like array j, and we remove it from the set, so we say like we remove it, and while like this array j equals to left, we just move it to the right. So for instance, right here, so x, y, y, and z, the left one is x, we remove it from the window, size should be increased, and it is it is moved one position to the right.
Yeah, I think in broad strokes it works. It's reasonable. Um, this approach should scale with other variations of the problem as well, where the array may not have everything which is unique.
But it says that the array contains only unique integers,
Correct.
characters. I mean.
Yes. Right. But you can in future, I mean, the solution that you build can use instead of a set, can use a map as well to keep track of the count of the characters.
Sure. Yeah, exactly. Sure.
And for characters, it's best to imagine them as literally integer indexes and store that into directly into a character array, is what I'm saying. So essentially, it becomes a character array that you're keeping track of instead of a set.
Okay.
Yeah. And what do you think? What is missing currently?
It's missing. Okay, let me see. Okay, we added. We check if it's in the set. If size equals 0, it means we get all the characters. We replace it. Okay, we remove it while size. Okay, y, y, and z. Yeah. So far we don't have like this result in initial string.
Yeah.
So we should like think
Yeah.
what it should look like.
And maybe you can fine tweak, you tweak the logic a little bit as you start writing the code as well.
Okay.
Yeah.
Uh, yeah. So okay. Let me check. Like when we remove x, okay, we add like y, which is already there. If it's there,
Yeah.
okay, it doesn't change. Okay, y plus okay z I x. Okay. Y. Yeah, and for like this example, it shrinks to like z, y, and x. So I think
Yeah.
yeah, I think this approach should work.
Okay. Okay. Do you want to code it up like in syntactical Java code, or you
Sure,
think
yeah,
this is fine?
sure. Let's try. Okay, so yeah,
Yeah.
I'll just follow these steps. So we have like a set of characters,
Sure.
which is empty by default. Then we have like
Mm-hmm.
three variables: int I equals to 0, j 0, and size is length of the array. Then we say like while
Mm-hmm.
j is less than the length of a string. Okay,
Mm-hmm.
we say like character right, so like j will keep track of a right character. It is character at position
Mm-hmm.
j. Okay, so
Mm-hmm.
okay. Yeah, so then we have this if statement. So if say contains this right character, it means, oh no, if it doesn't contain. So if there is no x so far, we
Mm-hmm.
say that the size, like the last remaining elements, is decremented by 1, so there is no more
I see.
3 elements left by 2.
Yeah.
And we add like this right character to this set,
Sure.
and yeah, so we do that like for x, for y. Yeah, so this condition works fine. Then once we,
Mm-hmm.
yeah, once size equals to 0, it means that there are no more elements left.
Mm-hmm.
And in this case, okay, yeah, so we get like character which is on the left, which is character on position I. We uh,
Mm-hmm.
we remove it from the set, so
Mm-hmm.
right, like that, and then okay, yeah, so we removed it, and yeah, we should shift our I like I boundary to the right. So we say while character at position I equals to this left, because there might be several characters
Mm-hmm.
which might be like just like repeat each other, and yeah, so before that we should have some some string which is our result, like the substring, and uh, yeah, I will just do like this result string, which will be by default uh, is empty, right? Because in
Yeah.
in some cases we just return an empty string.
Sure.
Okay. Okay. So if our result length is equals to 0, it means that there is no any substring yet. And we just simply say that the result equals to s substring, this like I and j window. And otherwise, we say that, oh yeah, and in other case, if s substring I and j length is equals, I mean, is less than the result, we replace it. So we say that result equals to s substring of I and j.
Mm.
And finally, we increment the left boundary by 1. So yeah, so that the whole window moves to the right.
Mm-hmm.
And and what else? Okay. Yeah, and we remove it from the set. Yeah, and right here we say that the size is bigger again because we, like, in future we will have some elements left. So it got smaller. Now it gets bigger because we remove this
Yeah.
like left element.
Yeah.
And I okay. Okay, okay. And also we need to increment our j position by 1. Okay. Yeah, so we should do that right here, so that
Mm.
when we use substring method, it gets our like this substring window.
Mm-hmm.
And finally, uh, okay. Okay. Yeah, I think we just return our like result. Okay. So I think that's like the optimal solution. Let me see if that like works for like this example, and maybe I can come up with some other test cases.
Okay.
So our string result is empty by default. We have like a hash set to keep all the characters inside of this set. All like pointers I and j are 0. Size is the array length of the array. Okay, so while j is less than strength of the length, we get the right character, which is x. If there is no x in the set, we add it and make like the size equals to 2. Okay, then we increase the window. Okay, yeah, okay, same for I and z. Okay, so far it's good. Finally, when size is 0, I mean that means we have our window. We get the left
Mhm.
character, which is x. We remove it from the set. We increase the size, and while the left character is x, uh, we yeah. So while it is true, yeah. So we just find the smallest substring, and yeah, and increase our left like boundary. Okay, okay. Yeah, so I think this solution should work for the example. And for instance, let me just think if our example was different, like this.
Yeah.
So as you can see, like there are like three axes in the beginning. So
Mm.
our window gets like we add x to the set, uh, size increased by 1. Okay, then it doesn't do anything here because it already contains the x. Okay,
Yeah.
then it adds z and y. Okay, so in this case, yeah, we have all the string inside of the window. We get the left character, which is x. We remove it from the set, size increased by 1. Yeah, and using this while loop, we move our I pointer to the Z position because as you can see there are like multiple axes right here in the beginning.
Yeah.
And okay, and we just yeah, and for every substring which is less than the length of our result so far,
Yeah.
we just replace it because that is the what we're looking for. And
Yeah.
finally, when j is at the end of the string, it means that we have processed the whole string and we just can return it.
Sure. And you're incrementing I within that while loop as long as I is the same character
Yes,
without touching J on that case.
yes. So while we get the character on the left, like x here, and while this
Yeah.
every left element is x, we should just go further to the right.
Okay. And you set up result within the while loop. Although your size had become 0, you could have had set result right there. But that's a minor tweak.
Uh, You so you mean like we can just return the result right here when the size is 0?
Not necessarily, just set the result maybe. Not necessarily return, although there are conditions in which you can you can return the result as well, depending on the length that you have seen so far.
Okay.
Yeah. But I think this is fine. It should work. And the
Um,
approach is fine as well.
yeah. So we get like we deal with all the duplicates in the beginning, and for
Yeah.
example, in the problem like text it also works. So I think we could just run tests and see how it performs.
Yeah, unfortunately, Pramp solution doesn't work. It will not execute.
Oh,
It will throw timeout on you, but this is fine. So you'll just basically initialize array and string and call within your main method. But um, we generally we start off by creating a pattern as to how our main method would call the
mm-hmm.
function that we are writing, and then go about actually optimizing the method or the code or algorithm.
Okay.
Yeah. Any questions that you may have? If none, then I think I got the answers that I was looking for.
Okay, yeah, actually, like I had a question, like for a different problem, if we could have some like non-unique characters, but you already gave an answer to use a map for that problem.
Exactly.
Okay,
Yeah. Yeah. So
okay.
we can swap roles if we are happy to go to the next problem.
Sure, yes. Let's swap roles.
All right. Thanks. Give me a minute. I'll go
Sure.
through the problem. I see. So from start to destination, we're counting the total number of passable paths on a grid.
Yeah.
Okay, I see. I see. Hmm. So it needs to maintain I greater or equal to j.
Yes. Yeah.
So at each point, we only have valid positions which are either northwards or eastwards.
Yeah. So we can go like only to the right or upwards.
Correct.
Yeah.
So, okay. So let's see that if n equals 4 for the given problem,
Hmm.
we have five answers, five ways to get to the destination. So you can continue to go north and then east, and then continue to go to, like, for example, in this case, 4 or 5. I see. So when the E character stands for moving one step east and the N character stands for moving one step north, so in the plot sequence E stands for the following. Is not no. Okay. So we're on a grid, and each move requires you to maintain I is greater or equal to j while you are selecting j. So you start off by starting with I and j equals 0,
Yes.
and you
Yes.
have to go to n by n,
Mm-hmm.
and how many total paths exist. So when the question is how many such total paths exist, we can either take BFS or DFS. It doesn't matter. We're just counting
Mm-hmm.
the total number of paths. And so what we're doing is we're basically saying that from each position, I can I can imagine a sort of like a tree-like structure starting with the source or start point, where I could have had gone two different paths, and then from those two I could have taken two more different paths, and so on and so forth.
Yeah. Yes.
And so then the path that yields the destination is the one that is considered as complete, and we have to give the total number of paths that lead to the destination. So so in each case, um, we're either crossing off the grid and we're basically calling off the search, or we're hitting our destination,
Correct. Yes.
right? So basically what we are doing is that now there could be an analytical solution here as well, but that would essentially become a single equation. I'm actually going to solve it using some sort of a recursion,
Okay.
right?
Yes. Yes.
So uh, so what we can do is we can imagine that if my problem was simpler and I had only a sort of like 2 by 2 grid, the start was 0 0 and end was 1 1, how many paths I could have had taken? 0 0 to 1 1, right? I could
Oh.
have had
Mm-hmm.
gotten to, so I'm just going to solve it for a 2 by 2 grid
Mm-hmm.
and say 0 1 to 1 and 1, 0 0 to 1 1 would require me to either go directly in one step. From 0 0 to 1 1 I can go directly because it maintains that j is less or equal to like
Yeah.
I is greater or equal to j.
Yeah. However, like for this problem, we can only go to the left or upwards, so we cannot go like in diagonals. Only like two options.
Yeah, but wait, so if I go from 0 0,
Mm-hmm.
then I is greater or equal to j. That's the only condition that I need to meet, right?
Um.
Oh,
Yes.
it also cannot cross the diagonal border.
Yeah. So that's basically
It
all.
cannot cross the diagonal border.
Mm-hmm.
So I equals to j is diagonal, right?
Yes. That's
But
like
it
the
does not. It's
condition.
not supposed to go right. It's not supposed to go on the other side of the diagonal. Is
Uh.
what I read it as.
Uh. No, it cannot go there.
Right. Right. But so to your point, if we are at 0 and 0, we cannot direct path to 1 and 1.
No, we cannot do that.
Yeah. So we can either become 1 0
Mm-hmm.
and 1 1, right?
Yes.
and there would not be any other path.
Exactly. Yes.
So for the 2 by 2 grid, we'll have one path.
Correct. Yes.
Okay. And so let's say that I try to decompose my problem such that when I am at, yeah, so 2 by 2 is essentially a representation of n by n. The same pattern is going to hold, and it's just our decomposition strategy, how we decompose it now. um, 2 by 2 is a simpler, I mean, obviously, if anything smaller than that, 1 by 1 is, it has a trivial solution. That start is already at end and there is only one possible.
Mm-hmm.
There's actually no, like, how would you return? Do you want to return as 0 because the source is already at the destination?
Yeah, you just return one.
So if n is less than 2, then I just return 1.
Yeah. Yeah.
Else what I do is I figure out what are my right moves from here, right? So I can go up,
Mm-hmm.
which means my, um you know yeah, so let me think now,
Sure.
how do we want to turn this around?
Okay.
So the basic skeleton is just going to be, and we're just going to print out. Okay. Now, so we got 4 by 4, and we can either go bottom up or top down. So I'm deciding to go from top down. So assuming that, I'm looking at 4 by 4 grid, and and one legit path for me is taking, um, yeah. So how do I keep track of I and j is something that I need to devise here. So one thing that we can do is we can say that, hmm, yeah. So say for example, I can do a simple grid search in this case.
Okay.
What I do is I say that for, yeah, how do I, just give me a sec. So let's say on a 3 by 3, I'll have how many such paths possible? I'll go 1. On a 3 by 3, just give me a sec. We have 1 and, mm-hmm. Okay. Say, for example, I decide to go from 3 by 3 grid
Okay.
to 2 by 2. And the way I do this is, how many 2 by 2 do I get? I have legit 2 by 2 are basically, yeah, so kind of till I hit destination. So basically what we need to do is we need to start off a basic grid search and say that if, let's assume I start off with the I being set, like the start point is obviously both of these are at 0 0,
Mm-hmm.
right?
Right. Yes.
So let's say that my start is 0 and 0. So I say that I go to start and my destination is n minus 1 to n minus 1, right? So this is how we're going to write it, that our final point is n minus 1 to n
Correct.
minus 1, right?
Yes.
And um, so the basic algorithm essentially is that iteratively we're we're counting all legal moves and try not to repeat the computations that we have done before.
Okay.
So if we start with I index essentially pointing to my row of the grid, and j pointing to the column of the grid,
Mm-hmm.
then I can do something like this:
Okay.
enumerate through all legal moves and count the ones which are actually ending with n minus 1 at. So sorry, j would be starting with the column. So j is my column index,
Okay.
and it's iterating through all potential columns. And so the legal move for me is only if j is starting off with the current value of I and is less than that.
Mm-hmm.
So you know the way we're looking at this is that only when J is less than I, that our progress is only in those cells when J can move up or yeah. So J is for moving up and I is for moving eastwards,
Okay, okay.
right? And and so yeah. So now what happens is that what would be the condition where we'll say that we have reached the destination?
Uh,
Um,
yes, so this condition is when your I and j, like you mentioned before, equal to n minus 1 and n minus 1.
Correct, correct. So anytime you actually have looped through the entire possible, like for each value of I,
Okay.
you, yeah, so you, the way it should be considered is that they both have to be incremented in conjunction. So instead of a grid search, it essentially becomes um, a two pointer approach that we have I and J.
Okay.
So let me sort of like nail down the basic structure here. But it is in the end a grid search, and so while I is less than the destination and J is less than the
Mm-hmm.
destination grid column, we're 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 taking a step towards I plus one as one legal move, and J plus one. Sorry, for all possible values of J which are less than I am taking one more move. So essentially, as I am increasing the value of I, as you can see from this these blackened grid boxes, that I can now have more legal moves in terms of J's positions. So uh, the way, yeah, so for example, for start position of I equals to 0, J will not have any other move. I needs to go, or yeah, so I needs to be at 1 before J becomes, sorry, I needs to be at, yeah, the very first black box appearing is at I equals to 1 and J equals to 1, like this first one.
Uh-huh.
But that one is represent, so what are the coordinates for, yeah, so this is actually,
Yeah,
yeah, I
0,
mean,
1.
I am referring to one. So there is one which is 1 and 1. That's not a legal move. And then there is 2 and 1. the 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 box between vertical axis 1 and 2.
Mm-hmm.
So the point is that it's going to be a DFS where we're incrementing J to all positions below I, all positions less than I, right? And and if J becomes greater or equal to N, then we break. And what happens is, if we have fortunately moved to a location where I is n minus 1 and j equals n minus 1, then we do count plus plus,
Correct. Yes.
and then we return count.
Okay.
That would be the basic sketch here.
Okay. So far, you mean like you mentioned before DFS, but you didn't implement it here.
Correct. Because I mean, we can do that if we have a helper function. Say if I track I and j here,
Mm-hmm.
if n is less than 2, return 1. If I is greater than um, so we need to maintain the global size, right? So this is why the pattern is slightly different, but you can imagine that if we know that there is a global grid size,
Okay.
then we break there, sorry, return from there, that point, and return empty. That's not a valid point.
Mm-hmm.
That's not a valid solution. Or similarly, if j is greater than size as well, then we return 0 from that point of
Mm-hmm.
view as well.
Correct.
And if I and j are actually, then we return 1, right?
Correct.
Right. So what we're doing is we essentially then now in this whole logic, so this is the same thing. Instead of doing iteratively, we can actually call this method with all legitimate values of I and j, or basically say that um, you know, that just for each iteration, I am um, I am decreasing the size of the grid and increasing the values of I and j that I'm going through. So size is the size of the grid. So let's say this is recursive, and so there is also and now in the recursive we essentially do all the logic.
Uh-huh. So just
We start off with our source being 0, right?
0. Mm-hmm.
And our size is already set. And instead of doing this decomposition where we are iteratively doing the same thing, what we're going to do is essentially call ourselves back up and increment the value of I. So there are only two possible directions that I can go in, right? So
Yes.
I'll say that int sum is this guy um, going from so I plus one and j, there is one, and the other one is um, I have I plus one and j plus one only if so what are those two positions? So if I equals to j, I need to return from that as well.
Wait.
So
So you return 0 here, but when I equals to 0, it still satisfies the condition.
now, so what that means is, but cannot cross the diagonal border,
Yeah. So
right?
if it was like strictly, if it was strictly greater, it means it went above the diagonal line. But if
Yeah.
it's like I, if it's greater or equal, it's acceptable. So yeah, this
Yeah. Yeah.
condition.
So we can say that if I is less than j,
Correct. Yeah.
that is not a valid path.
Okay. So you also mentioned before that we can go only like to left. I mean, sorry, to right or above. But
Correct.
I think like your second recursive call, you try to go instead of like, so for I you go to one direction, but here you seem to go in a diagonal, right? Because you increment
Yeah.
both a row and a column here.
Yeah. Yeah. So the way it should actually write is that it's actually I plus two and j plus one,
Oh, okay.
because if you think about this, that I is equal to one and sorry, let's say I represents my in this case, unfortunately, visualization starts with the x-axis. So let's say I represents x-axis, then when I is 1, j cannot do anything. I was 2, j could be 1.
Okay.
So
Yeah. Yeah.
eh,
But
I equals to
sure.
3, j was 1 and j was 2. So strictly what we are actually looking at is that j is always less than, yeah, since it is not crossing, yeah, the condition is less or equal to, and so we're basically restricting our grid search in the same direction. And in order for me to increment j, I need to give I one more.
Yeah, but still it seems strange because
Yeah.
you seem like in the first recursive call you check the next row, but you seem to skip the next box in the same row, but in I believe in another column, right? Because You just move like 2 rows ahead, but you don't check the next column on the same row
Yeah.
in the second call.
S- Uh, so you're referring to if you point to x and y coordinates, which you're talking about x equals to 1,
Yeah.
and
Mhm.
what are the possible values for y or j, right?
Yeah. So imagine if the x-axis is I and
Yeah,
y-axis is j.
yeah,
So right here you call the method for I plus 1. So you check the uh, so yeah. So you check the box to the right. So you check the position 2.0, right? Because if we imagine
yeah,
uh,
yeah,
is in x-axis is y I. But
yeah.
uh,
So I'm actually checking for all potential values of y which are going to maintain the condition that we have. So you're going up,
mhm,
or your j can so what we can say here is that you can go up or you can go eastwards, right, which is j plus 1,
mhm,
right? And but the condition that needs to be met is that if I becomes less than j, then we return 0.
yeah,
So this would be that condition.
correct, yeah.
Yeah,
But just yeah, if you look at the box which like says 1 comma 0, the example,
yeah,
uh, you like you just mentioned. So in this college right here,
yeah,
you check the box next to it to the right at position like 2 comma 0. But right here, uh, oh yeah, right. So we should also like fix I mean check the one above it. Yeah,
correct,
and oh yeah, and the condition is I mean like this specific condition. Sure, correct.
exactly,
Okay,
yeah, yeah,
and you return some. Okay,
yeah.
correct. Okay, sure.
This would be the basic building block for us. I can do some uh, it's a DFS, and there are path prunings which are automatically happening only when we complete the whole path, then we are returning with a sum.
Mm-hmm.
So so for each value of I'll have j iterating through less or equal to I for potential next transition. So it's n into n minus 1 kind of um,
Mm-hmm.
traversal.
Okay, and like so far for the DFS function, can you like assess what the com- time complexity and memory complexity for like
Yeah,
any n?
correct. So for each n, we have n squared total number of uh, uh, grid,
Mm-hmm.
blocks. So for n squared blocks, we have to traverse about n squared over 2 because of our search pattern is not letting j grow in all the directions.
Mm-hmm.
And so it still is going to be in like asymptotically, it's in the same the total number of nodes plus edges is what we look for, and
Mm-hmm.
nodes are n, and edges are going to be n over 2 essentially.
Okay.
So its order of v plus e essentially becomes n plus n over 2, so it's linear in terms of my overall uh, blocks that I'm visiting.
Mm-hmm. Okay, but however, I see like that in this problem, it seems like uh, you see like inside of your dfx function, you
Yeah,
have two more calls, and you do this for every like for every
correct,
dfs call, you do the same. So basically, it looks like a tree, right?
correct,
So
correct.
it looks like a Fibonacci function. So the complexity, like, are you sure about what you said before?
Right. So, but there are going to be early terminations for many of these paths. So we do create a search path, but we return very fast, or we can not grow. We can decide not to grow as well by putting the condition here. We can say that only go to j plus 1 if j plus 1 is less than I.
Mm-hmm.
And so the growth, it's kind of like natural backtrack, what we call as early termination, essentially. We're not
Mm-hmm.
backtracking, but we're early terminating in most of the false scenarios.
Oh, okay.
And we are not, yeah, so the goal is going to be that we should not be revisiting the same block,
Mm-hmm.
and that can be dealt with. I think the growth pattern is such that in many of these cases we should have an incremental gradual, so no two values of I and j should be called essentially in our recursion.
Mm-hmm. Yeah. Okay. So as you can see, like, the problem says that the constraints for integer r is from like 1 to 100,
Yeah,
and okay. So uh-huh. And also, oh, okay. Yeah, and your like dfi function still, it seems like the
yeah,
complexity will be, so the
yeah.
complexity of the problem will be like 2 in a power of n, just like a Fibonacci
if
problem.
if it was not, yeah, if, yeah, yeah, this is conceptually correct.
Okay. Uh, yeah, because for yeah, just imagine like if you have like n equals to 0, right? So you have like 10 by 10 grid,
Yeah, yeah,
and the time complexity will be just like 10 to the power of, I mean 2 to the power of 10, which is like 1000, right?
yeah, yeah,
And it gets like worse if you have like 20 or 30 or like 100, as they say
yeah,
here. So I think like the recursive function will take you like lots of time. So
yeah.
you,
I mean, think about the same, so it's basically, if you think about that grid search, that the iterative solution that I had written, right?
mm-hmm,
It's basically that. So for each value of I, we're iterating all the way up to I, right?
mm-hmm,
So that kind of a growth pattern essentially is in asymptotic analysis. It's n squared, not
yeah,
necessarily. It's high. It's n squared domain essentially.
correct, yeah,
Yeah, and so that's why I was saying that it's in the now the total number of blocks are n squared, right? And
mm, yes, yes,
we have to visit based on our growth pattern. We're filtering them out. If I were to go, um, so this requires a full answer, right? So we need to provide all possible paths,
correct, yeah,
right? So we cannot take any greedy approach.
mm-hmm,
That means DFS has to be done, or BFS has to be done in all, at all levels. We cannot, Yeah. So so what you're saying is that there is a better solution possible?
Yeah, so because like this one, we can either um, save a number of ways. So for instance, you start like
Yeah.
from 0 0, and
Yeah.
but for each like I and j pair, you can save this basically like variable sum.
Correct.
So you can
Into a
save,
memo.
right. So
Into
instead
a
of
memo.
like doing the like work over and over again, you can like
Yeah.
save some of it,
Correct.
and you can definitely improve it.
Yes, exactly. So memoization would definitely help here.
And
So then all the values of J which have been pre-computed would not be recomputed.
mhm.
Yeah.
And exactly, yeah. So I think like this way, like your solution will just get like that number of like paths and use
Yeah.
it for this variable, another variable sum.
Correct. Correct. And memoization is a very simple, um, essentially, all we have to do is to declare a map, right?
Right.
And initialize it. And then anytime we return the sum, we're actually for all the values where we are returning, we first, so the pattern becomes for what I want to do is construct a key which is essentially a string of n I n j,
Mm-hmm.
and put my answer for that key, and anytime I see that for the values of I and j that I'm calling back again, I return the answer from the memo.
Yeah. Right.
So that pattern can be easily accommodated here.
Okay. Yeah, that's because like this function otherwise take lots of time. So the one that you just mentioned, it's a great improvement here.
Got it. Got it.
Okay, and one more thing right here. So
Sure.
are you sure that the like the key of your map will be just into one single integer?
it the key to the map is the new starting point, essentially, right? So for each starting point we'll have one answer,
Right.
right? So that starting point is composed of I and j. Simple as that.
Mm-hmm. But how does it know a difference between like I and j? Because it's just a number. It can be there can
Yeah,
be like row number one or column number one.
right. So I was thinking of literally creating I equals I and j equals j string value, essentially.
Oh, okay.
Yeah, like literally calling it as I equals
Mm-hmm.
like this,
Okay.
right?
Okay. Yeah.
And then j equals j. So this essentially becomes my, sorry, this essentially becomes string. Yeah, I understand why you were confused.
Okay. Nice. Yeah. Yeah. This is much better. So now we can like see a difference between I and j, so we can know like the precise position.
Exactly. Exactly.
Okay. So okay. I and j size. So yeah. So now with all the improvements and memorization, uh, it will work much better.
Great.
Oh, and also like when you put your like your value, you should also like use it somewhere, right? To make
Correct.
further calculations better.
So if I say that if, yeah, so I say that string p is essentially this guy, right?
Yeah.
and if memo dot contains key
Mm-hmm.
key, return memo dot get key,
Correct. Yeah.
and memo dot put key one,
Uh-huh.
memo dot put key zero, uh, and and so forth,
Correct.
essentially.
Okay. Yeah. So now this is like much better. So
Great.
okay. So yeah, I mean, you improve all the DFS and mhm. Yeah. So now, like, no matter how big the n is, because like
Yeah.
mentioned, it can be from 1 to 100. Uh,
Yeah.
you, it can easily get like the value from the map, and
Great.
yeah, now it will work much better.
Sounds good. Thanks a lot.
Yeah. Thank you. Also.
Thanks. How's your job search coming along?
Well, I'm actually like a student, and I'm looking like for internships for like next summer,
Great.
and they started opening like positions. So
Right.
and like I'm trying like to do like those mock interviews in advance just to get
Yeah.
some experience.
Yeah. It's very helpful. I'm actually I'm planning to do an active search in a
Uh
couple of
huh.
months time and using Pramp to sort of like, when you're actual software engineer, you're not doing many of these things on daily basis,
Yeah.
unfortunately. So it's always needed to get into rhythm. So I'm sort of building up some rhythm.
Nice, nice. Yeah,
Right.
I also noticed that for me sometimes I'm doing like private interviews just for my emotions because sometimes I can just get easily nervous and
Yeah, yeah.
that's has been a problem for me like for my whole life like in high school in college all the
Yeah.
time.
No, no, no. First of all, I think it's all about us giving, like, that happens to me as well, by the way, and
Uh-huh.
that problem is easier said than done in terms of, that we can somehow fix nervousness. For anything that is important to us, we're going to be nervous. If this
Yeah,
something is not
exactly.
very important, then we're probably going to be less nervous. So
Yes, exactly.
so yeah, all the best, man. And hopefully we'll see you again.
Sure, thank you, and
All right.
have a good luck on your like future applications.
Thanks so much.
Thank
Take
you.
care. Bye.
Bye. Так, ну чё? Ну чё? В общем, так, камера. Сейчас покажу все, что тут произошло. Короче, понаписал я тут целых замечаний, да, внизу вот. Сейчас я все расскажу, что все это значит. И вот на втором листе это примеры какие-то. Сейчас будем разбираться. Так, в общем, даем фидбэк, да? Вот, я все-таки узнал, меня тут это интересовало. Так, ну что, погнали. А, RAW Solution. Ну, с подсказками он сделал, да. Так. Вот так вот мы поставим. Do well. Came up with a BFS and an improvement solution. Awesome. Ну вот, короче, ошибка эта совершена была. Сейчас я опишу, какая. And later and improved solution. Так, я сохранил вот это, надо сейчас протестить эту задачу, короче. Так. Что еще написать-то, ё-моё? Came up with defense and later an improved solution. Also figured out all the edge cases like IJ. It would be better to completely read the entire problem, write down all the conditions, and write a rough solution in comments in advance. It's a bad practice to try to come up with a solution while coding by changing lines around, variables. Так, ну я все по делу пишу, в принципе. Well, variables and if statements. Все, в принципе. Using, не-не-не. I think there should have been some test cases. The solution, the iterative solution seemed vague and no test. And the switch to ifs was sudden and rapid. Что это? Окей. Explained everything well and made some notes for my performance. Так, ну тут ответ нет, короче, это 100%, потому что, как я писал выше, минусов много, и интервьюер за это зацепится со страшной силой. Потому что, ну типа, сначала нужно придумать решение, а потом пытаться его сделать. Да. Медиум. Все по делу, в принципе. Так, прочитаем, что про нас сказали. О, 4, по 3 звезды, нормально. Just more practice, ну да. Окей. Все, такие вот дела. Проверим решение мое. Короче, я там сначала затупил, правда, но бывает. Вот, у меня все решение в комментах. Я потом чисто комментарии свои превратил вот в это все. Смотрим, как там было-то. Сейчас я посмотрю. Нам нужно строчку найти, да? Значит, это значит... нет, у нас массив сначала. Char равно x, y and z и string str. Это вот все дело. Готово. Так, get shortest substring. Char str. Ой, что не так. Должно быть z, y, x. Так, система println, точнее. Так, я тут ошибся с этим, короче. Ага, что-то неправильно, смотрите. X, Y, Z, X, Y, Y, Z. То есть он не меняет, как сказать... Он находит самый неэффективный вот этот вот фрагмент. Сейчас. Ага, так. Интересно. Так. Угу. Так. X, Y, Y, Z. Дальше. X, Y, Y, Z. Блин. Y, Y, Z, Z, X. Ага. Понял. Угу. Черт. Ошибочка. Всего лишь одна строчка вот здесь. То есть он берет тот пример слева, да. Как там сказать это, блин? If set contains. Короче. Что за дела? Бля. Значит, все-таки мап нужен. Да, получается, нужно с помощью мапы сделать. Но все равно я был почти близко. Можно, конечно, попытаться сделать map character integer. Map равно new hash map. Так, вот это все снести, короче. Тут надо заново думать. Так. Короче. То есть, что мы делаем? Ага. Ну да. Ну, сейчас можно на самом деле вернуть это все. Так, это... Так. Size, окей. If map contains key right, size минус, нет, map put right, map get or default right or. Вот. Потом мы J увеличиваем. Дальше. Ага. Так. Если map size равно blank, так. Так, ну-ка примерчик еще раз. Оп. Так, x 1, 2, 3. Опа. Так, у нас получается, вот мы нашли, да, left. Если, точнее, сейчас я это отредактирую. Сложно смотреть. Так. Другое дело. Так, получается... Ага. Если map равно... Ага, так. Char равно это. Если set равно... Так. Frequency равно map get left. Если у нас... Стоп. Если frequency равно нулю, map remove left. Else map put left frequency. Так. Ну вот. Size плюс, так как мы удалили все имеющиеся элементы. Блин, да, надо было так делать. Ага. 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 Так, 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 так. Ага. 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 Так. Ага. Ага. Ну вот, уже намного лучше. Другое дело. Можно попытаться это запустить. Сейчас мы проверим на примере на нашем. Так, короче. Что он мне тут наформатировал? Так. X не содержится в мапе. Добавляем. Отлично. Size, все правильно. Добавили. Прибавили. Отлично. Это все правильно. Добавляем Y. Ага, опа, так, мы добрались до этого окна. Получаем x минус 1, если равно нулю, значит мы его удаляем, правильно. Так, иначе просто уменьшаем, правильно. Так, это все правильно. Дальше. Ага. Y. Нет, не содержит. Нет, содержит. Прибавляем, окей. Ага. Опа, так, вот здесь что у нас? Z. Ага. Так. SWE. Все, я думаю, вот это заработает. Должно. Да, проверяем. Отлично. Заработало. Но все равно нормально. Я хотя бы, хоть я и неправильно сделал, но в том направлении двигал. Мне осталось бы поменять просто парочку строчек. Да. Все равно нормально. Вот, все правильно. ZYX. Сейчас мы попытаемся свой какой-нибудь придумать пример. Вот, допустим, мы вот сюда навтыкаем букв. И сюда. Что он нам выдаст? Все то же самое, отлично. А теперь как-нибудь вот так вот. Нет, неправильно. ZU. XYZ, да? Не, все равно Z. Ну да. Так, а если у нас здесь будет какая-нибудь А, Б, С, Д, Е. Какая-нибудь такая хитрая строка. А, Б, С, Д, С, Б. Что-нибудь найдет? Так, нет, что-то неправильно. не нашел. А сейчас найдет, да? Меня все равно не находит. Чё? Интересно. Блин, это ж я... Потому что так нельзя делать-то, ё-моё. Что я туплю-то конкретно? С... Повторяется. Почему у нас опять неправильно делается? С, Е... Не так. Что-то я в затыке. Ну да, map это правильно. Блин. Ладно. А как он это находит, непонятно. Раз, два, три, четыре, пять. А, ну все правильно. Короче, я настолько вообще затупил уже. Все правильно, этот ответ правильный. Я сижу, думаю, почему он неправильный. Он правильный. Все правильно. Все правильно, да, все правильно. Е, С, Д, Б, А. Все правильно, все правильно. Короче, этот ответ, это решение можно добавить себе в... Куда? В слайдинг window. Не, все равно нормально я сделал. Даже если я вот здесь сделал неправильно с сетом, все равно я вот потом прикрутил пару условий, и все заработало. Поэтому мы это добавим в коллекцию. Так. Программинг. Сюда. Нет, куда? Мимо. Вообще не сюда, в алгоритмы. Сюда, сюда. Smallest substring of all characters. Smallest substring of characters. Вроде даже была такая задача вот здесь. Но я не... Ну, вроде что-то даже было. Не, ну что-то с мапом тоже было. Но это уже хард, попахивает хардом, кстати. Все равно что. С мапом. Так, ну ладно, вот на будущее тогда мне нужно смотреть больше на тест-кейсы, да? Потому что он думал, что вот это самое нормальное, оптимальное. Дальше он удалял из сета. А, вот он удалил здесь, а он еще вот здесь хранится. Угу. Ладно. Так что да, все отлично.